Okay. Good morning, everyone. Okay, in this video, we are going to discuss the first isomorphism theorem. The first isomorphism theorem. Statement. That is, let H and N be subgroups of G. Let H and N be two subgroups of G, and let N be normal in G. Then, so we need to prove 4 conditions here. The first one is very important. The first one is Hn is a Hn is a subgroup of G, and the second one is N is normal in Hn, and the third one is H intersection N is normal in H, and the fourth one is Hn by N is isomorphic to H divided by H intersection N. The fourth one is this one. So here the given that H and N are two subgroups where N is normal, that is N is normal and H is subgroup, we need to prove for these conditions. Okay, so we proved one by one. The first one proof. So the first one is, so to prove first one, first we have Hn can be written as union of An where A belongs to H. That is set of all cosets of H in N. So that is Hn can be written as union of An where A belongs to H, and this can be written as union of Na where A belongs to H. Since the reason is, since given that N is normal, right? Since N is normal implies what? Every left cosets is equal to what? Right coset. We have a theorem, N is normal if and only if every left cosets is a right cosets of N in G. So from that one we can write union of A can be written as union of Na where A belongs to H, which is nothing but N into H. So we proved that Hn is equal to NH. Okay. What we need to prove that? We need to prove that Hn is a subgroup of G. So from this implies Hn is a subgroup of G, right? We have a result, Hn is a subgroup of G. So we have a result that I mentioned. I write the result here. The result is H and K are subgroups. H and K are subgroup of G. Then product HK is also a subgroup if and only if HK is equal to KH. So from this result we can conclude that Hn is a subgroup of G since Hn is equal to NH. Okay, so we proved the first one. We proved the first condition, that is Hn is a subgroup of G. So now to prove that the second one, to prove that N is normal in H. So that is let G Hn elements of Hn is of the form, right? Some G into N. Okay, I am taking that some G into N belongs to Hn and some N belongs to N. implies that this is for all gn n gn inverse belongs to H. So this is our A. Okay, so first we can see as n is normal, and therefore n is a subgroup of H. First, to say that n is normal in Hn, so before that we need to prove that n is a subgroup of G. But clearly n is a subgroup of G. N is a subgroup of Hn. Sorry, n is a subgroup of Hn, and we can easily prove this condition. That is, consider Gn. Okay, we consider this one Gn n Gn inverse, like this one, where G belongs to G, n belongs to n. But in place of G we have Hn, right? And which is can be written as G into n and Gn inverse. Okay, here Gn is nothing but what? It's an element of what? It's an element of what? H. Okay, and this is an element of what? H. Sorry, this is an element of n. This is an element of H. This is an element of, sorry, Hn. This is clearly an element of Hn. This is a clear an element. This is a clear. So since Hn is a subgroup, we can conclude that these things are indirectly in Hn. Therefore Hn is normal. Sorry, n is normal in Hn. And the next one is the next condition to prove that next we prove that H intersection is normal in H. Since H is a subgroup of G and N is a subgroup of G, H is a subgroup of G and N is a subgroup of G, therefore H intersection N is a subgroup of G. Subgroup of H, we can directly write this H intersection N is a subgroup of H, since the reason is H intersection N is contained in H, which is a subgroup, okay, which is a subset of H, and H is a subgroup, and we know that this is a non-empty and intersection and their subset of H means it is a subgroup of G. We can easily show this one. We can easily show that H intersection is a subgroup of H. Okay, so to say that H intersection N is normal in H, so first we need to prove that H intersection is a subgroup of H. So we can directly say that H intersection is a subgroup of H. The reason is H intersection N is contained in H. Okay, for that one, take any two element. Let A comma B belongs to intersection N. Okay, implies that A belongs to H. Sorry, A comma B belongs to H and A comma B belongs to N. So now to prove that AB inverse belongs to H intersection N. H intersection N. Okay, that is so consider AB inverse. AB inverse, but AB belongs to I am considering this one. A comma B belongs to H implies AB inverse belongs to H, right? Since H is a subgroup, and AB belongs to N implies that AB inverse belongs to N. Since N is a subgroup of G, therefore AB inverse belongs to H intersection C, and where this is very important. Since it's a subset of H, therefore AB inverse belongs to H. Therefore H intersection is a subgroup of G. H intersection G is a subgroup of G. Now to prove that H intersection N, to prove H intersection N is normal in H, that is Hx H inverse belongs to H for all x belongs to H and H belongs to H intersection N. So this is our aim. Okay, for this consider, let H belongs to H and X belongs to H intersection N. So we have Hx H inverse belongs to, and this is an element of H, right? H, and this is an element of H, and I am taking X in H intersection, implies X belongs to H and X belongs to N. So this is an element of H. These three are elements of H, therefore this is belongs to H. And also, and Hx H inverse is also belongs to N. Why? Since N is normal, from the definition, since N is normal in H. This is from second condition. Therefore Hx H inverse belongs to H, Hx H inverse belongs to N. Therefore Hx H inverse belongs to H intersection N. That is H intersection N. Therefore we can conclude that H intersection N is normal in H. So we need to prove the last condition, that is very important one. So for that one, to prove that Hn divided by N is isomorphic to H divided by H intersection 1, I am using fundamental theorem of ring homomorphism. Consider mapping F from H to Hn by N defined by f of H is equal to Hn. So clearly F is homomorphism, no need to prove this one. Clearly F is homomorphism. Next, to prove F is onto, so for that one I am taking, let Xn, I am taking an element in image, that is Xn belong Hn by N, but this implies X is of the form some H into N, where H belongs to H and N belongs to N. Thus that Xn can be written as Hnx now, that is X can be written Hnx, and which is equal to, these are, N is an element of H, therefore since Nn is equal to N, if and only if N belongs to N, therefore Xn is equal to Hn, which is nothing but f of H from the definition. So therefore Xn as a preimage, therefore F is onto. And to apply fundamental theorem of first isomorphism, we need to find kernel of F, that is set of all H belongs to H, such that f of H is equal to N, that is identity here, and that is set of all H belongs to H. F of H means what? Hn. So that is set of all H belongs to H, which is nothing but H belongs to N. That is set, you choose elements such that which belongs to both H and N, this implies which is equal to H intersection N, that is common elements of both H and N. Therefore kernel of F kernel of f is equal to h intersection n. So by fundamental theorem, homomorphism, h divided by h intersection n is isomorphic to, what is the codomain here? hn by n. That is g by kernel is isomorphic to g dash. That is the, so this completes the proof.